The internal geometry of an inhaler plays a crucial role in how it functions. This image shows an inside look at the geometry and structure of an aerosol inhaler. Changes in the geometry impact the flow of the fluid. One particular feature of the inhaler that we will be focusing on is the atomizing nozzle shown here. This is a region with a very small cross-sectional area compared to the rest of the flow passageway. At the atomizing nozzle, the liquid medication is converted to dispersed liquid droplets, shown by the blue dots in the figure. Bernoulli's principle is an important concept in fluid mechanics. It is based on the principle of conservation of energy. According to Bernoulli's principle, as the speed of a moving fluid increases, the pressure of the fluid decreases. This is shown by the Bernoulli equation. This equation shows the pressure energy, kinetic energy per unit volume, and potential energy per unit volume. The Venturi effect is another important concept in fluid mechanics that is related to Bernoulli's principle. This phenomenon occurs specifically when the fluid flows through a constriction, or a smaller cross-sectional area. Here, the fluid velocity will increase. This is due to the principle of mass continuity. As the velocity of a moving fluid increases, the pressure of the fluid decreases. This is due to the principle of conservation of energy, or more specifically, Bernoulli's principle. The change in pressure of the fluid due to the constriction is known as the Venturi effect. In these scenarios, total flow rate stays constant. Let's return to the inhaler diagram shown previously. We are particularly interested in the atomizing nozzle and the chamber to the right of it, the mouthpiece. The atomizing nozzle has a narrow cross-sectional area, which then gives way to the larger area of the mouthpiece. We'll refer to these regions as Region 1 and Region 2. This diagram shows Regions 1 and 2 as described previously, with their corresponding cross-sectional areas, velocities, heights, and pressures. Based on Bernoulli's principle and the Venturi effect, we would expect the constriction, or Region 1, to have a larger velocity, and therefore a lower pressure. We will explore this mathematically.
In order to simplify the equations being utilized, a few assumptions can be made, including the cross-sectional area being circular and constant density. We can analytically make conclusions about velocity and pressure based on flow rate and Bernoulli's equation. As shown by equation 1, if d1 is less than d2, then v1 must be greater than v2 for the equality to hold true. Next, if v1 is greater than v2, then equation 2 shows that p1 must be less than p2. Here we have assumed that h1 equals h2 and ρ1 equals ρ2. There are several parameters that affect the pressure changes, including volumetric flow rate, diameter, and density. 3 iterations were simulated using MATLAB to better analyze their effect on pressure change. For the first iteration, D1 is the average atomizing nozzle diameter, a value which was found in current literature, and D2 is the diameter of the ProAir HFA inhaler. Because it is assumed that regions 1 and 2 of the actuator are aerosolized, the variable ρ was used to represent air density. As the graph shows, the larger the volumetric flow rate, the more pressure change there is. The only change in the second iteration are the values for D1, the atomizing nozzle diameters found in literature. The graph shows that the smaller value of D1, the bigger the pressure change. This indicates that the Venturi effect is greater when the atomizing nozzle has a smaller diameter. For the third iteration, the volumetric flow rate of 60 liters per minute was used, a value found in current literature. The graph shows that with a constant volumetric flow rate, change in diameter has a dramatic effect on pressure change.
The MATLAB modeling showed that pressure increases from the nozzle to the mouthpiece. The magnitude of the pressure change depends on both volumetric flow rate and the size of the diameter, and that there is a more profound Venturi effect when the nozzle has a smaller diameter. Due to the Venturi effect, flow from the smaller nozzle into the larger mouthpiece will cause a pressure change. This causes a partial phase change, turning the medicinal vapor into droplets for dispersion. This spray allows for better lung deposition. By manipulating the geometry of the device, specifically in the cross-sectional area of the passageway, the pressure and velocity of the moving fluid can be optimized to ensure a correct dose is administered. Assumptions made for this project may not accurately represent the true fluid dynamics of an inhaler. For instance, the mouthpiece area cannot be realistically modeled as a circle because it is typically oblong or ovular in shape. As the medicine transitions from a vapor to a spray, the density is not likely to remain constant. Developing a better understanding could result in more accurate dispersion and less wasted medicine.